Okay, so we're ready to start Module 2 here in the Design Projects for Engineers course. So as we look at Module 2 here, we're going to be looking at an ArborPress project. And some of you may have already started some of the models because I've had it out there before, so it's good to do that. But I wanted to kind of show you how things are structured here so we know kind of what the expectations are. So first of all, we have the learning plan, and we're going to kind of go back and forth to the learning plan. And in these first couple meetings, we're going to kind of get through, if you would, the lecture and the details, but there's going to be plenty of time for you guys to work independently each one of the nights that we're together. I'm going to have the session recordings out here. So this is the first year we're teaching this with the SolidWorks software. So I don't have any previous videos out there for you because last year it was a Creo class. So it's kind of like doesn't make sense to put those out there because it's not applicable. So those will be new as we go along. Then you're going to notice that we have two practice problems for Module 2. Okay, the first practice problems are going to be on dimensioning. These are the rules that you've been learning since your first term in the quarter or in the program, as well as, sprinkled along. I know if you took GD&T with me, this is the first like little assignment that I gave you guys, and it was a dimensions like review. So I think it's a good place to kind of bring all that stuff to the front of our minds again. And if something's not quite, in there, to ask questions and make sure we got it. So that's dimensioning. That'll be something that I'm not going to necessarily cover that stuff. It's kind of just like a review for you and then ask questions as you need to. The other practice problems we have are going to be a lecture that I do tonight. And this is going to be, I think there's some review here, but really kind of looking at tolerancing and fits in detail and making sure that we know how to apply them. And they're going to be applied to the ArborPress assembly that we have for the project for this particular module. Okay, so we'll see how that's structured after we do our lecture. Then you're going to notice that we have 4 assignments here. The first assignment is the part models. So as we look at the part models assignment, you're going to notice that I have part numbers for all of these elements. So there's a frame, a ram, and so and so and so. So you'll notice that there are numbers, point values associated with each. The frame is the most complex, okay? So that's why we're getting 20 points for that one. And then they range down to 10 points, kind of the simpler things, okay? So when you save these items, you are not going to save them as the file name. You're going to save them as the file or the part number, okay? And that's very typical of how you would save things out in industry. So I want to kind of give that flavor to how we're going to be doing things, okay? Requirement here, and we'll talk about this more as we get there, but the requirements here are that you expand out that design tree or you show that design tree, and I want to see all of the sketches expanded so I can see that they are all fully defined. If there's a minus sign on a sketch, then as we know, that means that it wasn't fully defined, and that's like job number 1. You have to do that, okay? I also want you to rename all the features in the design tree to be more descriptive. Okay, that's something that you had learned, in the last couple of classes. It's way nicer to try to figure out how you're designing something or if you're trying to pinpoint something by looking at the description of the feature as opposed to just a generic extrude boss base or something like that. Okay. And then I already said that you need to save those. So then kind of all those things. So that's going to be the model. So that's just the models, okay? Then you're going to do an assembly model. You're going to put it all together. You're going to have an assembly model, okay? But there's two models here. You're going to have one for the entire ArborPress assembly. And then we'll talk about this, but I want you to make a little sub-assembly. There's 2 parts that actually get pressed fit together. So it's a logical place to have a sub-assembly. So you're going to be doing a sub-assembly and a full assembly, okay? And you'll see those. Those are going to be screenshots. You are never in SolidWorks unless I'm like, I want to see your model or can you send me that? I want to see what's going on here. Doesn't happen very often. Screenshots give me everything that I need. And if you do send me the file, especially when it's an assembly, if I don't have the files all in the same directory, as you know, I can't access it anyway. So So if I would need to look at your models, I would probably come to you and kind of look at things, okay? So those are just screenshots. Then we're going to have detail part drawings as you would expect. So so here again, we're going to be saving these. We're going to be pulling up the files that we made our models of, and then you're going to be using WCTC borders on here, okay? Title block has to be fully filled out. You're going to apply the ANSI standards as we know it, and that's why we're doing some of that review right at the beginning here to kind of get those good drafting techniques and rules in front of our brains again. You're going to save it as a PDF, and then that's what you're going to upload. Don't take a screenshot of drawings, okay? Otherwise, it gets kind of grainy and weird looking. Models, yes, but drawings we actually save as a PDF, and then you upload the PDF, okay? And we'll go over how to do that as we get closer to that. And then you have an assembly drawing, okay? So here again, you're going to be having two assemblies. One is going to be a sub-assembly, and the other one is going to be the big assembly. And then applying all the rules, balloons, and all that kind of stuff to them. I think we probably do a section in it, if I remember correctly. So it'll be so fun to look forward to. So, so yeah, so that's really what we're doing in here. It's going to be looking at this ArborPress in terms of a full set of working drawings. So that's going to include both details with tolerances as well as an assembly. Okay, so a very traditional type of project. So let's look at our learning plan first, okay? So as we look here, you're going to notice that there's a handout, and I didn't make copies of them because it's kind of like 20 pages is for one, and another one is a significant amount of files. So we're going to reference the PDFs. I have them underneath my camera, so I have them printed out, but we'll reference the PDFs for you. If you want to print them out, or if I need to make copies for those who are in class here, I will. You can let me know if you want me to make those. I'll do those during our break, but I find a lot of people end up using the PDFs anyway, okay? So today is going to be dedicated to introducing us to the tolerances and getting to know the parts on our ArborPress, okay? The next time we get together, we're going to talk a little bit more about modeling in SolidWorks and how to do more of the challenging parts. The two that are probably the most challenging are going to be the frame and the pinion shaft. Okay, the pinion shaft isn't hard, but I'm going to give you, I think, a kind of a nice way to set it up so that SolidWorks does kind of a lot of the work for us. So, and then the frame we'll talk about. There's a couple different approaches that you can take on that one, and I think both are really acceptable. But we'll probably talk about that the next time we're together, just so that you know. So, so looking at fits and tolerances this evening, and then, like I said, starting on the models and such. And then the things that you're going to be handing in are the assignments that we had just looked at. Now, as we get going here, I think it's important to understand and know how an ArborPress works. So I have a working ArborPress here in the room. So if you happen to be in attendance in person, there's one on the table in front of here. And so it's not exactly the one that we're using or that we have the drawings of in the handout that I have here, but it has a lot of similar parts, okay? They just might not be configured exactly the same, but the way that it works as well. So as we get started here, what I want to do is I'm going to stop this for just a second. I'm going to turn that down a little bit. It seems kind of loud. So we're going to look at this video, and this video is just going to show us the operation, kind of animation of an ArborPress, just in case you may not be familiar. So I expect everybody to be paying attention and watching so that you get all the information here at the beginning. I'm going to make this full screen, and yeah, I don't have a premium, so we're going to watch this little thing here.
Have you ever opened one of my emails live?
All right, we're going to skip now. There we go. Okay.
Hey guys, Ben is here. Today I want to show you how to set up the 1-ton ArborPress properly. This machine is extremely heavy, so it's important that you follow these steps for your own safety.
Mostly I like the assembly of this because then you can see the individual parts.
You never want to place the press directly onto your table. For me, I use a piece of cutting board to avoid it from scratching my table. When you first receive the press, it will come disassembled. These are the parts that you will find in the box. You have the base piece, a ring, the handlebar, and also a pretty heavy piece of steel that goes in the middle of the machine. And on top of this, you will need additional item, which is the AKC mold. I recommend you having one large pan, the large block, and also you will need an Allen wrench. They normally come in a set. Most people have them at home, and within the set, there will be a size that fit the ArborPress. I forgot to mention that I do not recommend the half-ton ArborPress. You need the 1-ton pressure to properly repress your products. So first, we're going to take the base piece and we're going to attach it to the ArborPress itself. You'll notice that you can spin this part around. Just pick the side with the widest surface. That way your mold can sit on top of it. Now we're going to set up the mold to use as a guide for the placement of the handle. Take your large pan, place it inside the mold, and use the large block and press it completely down. You want to turn it over to make sure that it's completely flat. Now place the mold on the ArborPress and make sure that it's resting on the surface and not the empty space in between. Now grab the long steel piece that have teeth on one side and the other side is completely flat. You want to place the teeth facing away from you. This should slide up and down. And at this point, you want to line up that piece with the block so it's completely centered. And you want to check from the side and also from the front. Now grab the handlebar. You will notice that there's also teeth on this part. The goal here is to line those up with the steel bar with the grooves on it. So place the handlebar inside the hole. At first, it might not go in, but if you slightly turn the handlebar up and down, it will slide in easily. So it's important to understand that it's not about strength. You just have to wiggle a little bit, and once the teeth line up, it will slide in automatically. I'm going to give you an example what is not correct. If the handlebar is on the top, pointing at your face, it's too high. And what happens if you press that down, the machine will fall over. Also, we are not pulling on the machine. We are pressing on the machine. I'm going to give you another example, what is incorrect. This position is too low and you can't really press down. Now it's in the middle where it's pointing at your chest. This is fine and I used to do it, but I find it if it points down a little bit below your chest, that's the best position. Now grab the ring piece. You'll notice that there is a little screw inside the ring, and that's when you use the Allen wrench to tighten that. This ring piece go on the opposite side of the handlebar. And once it's tightened, it will prevent the handle from accidentally fall out. If you receive the machine and you don't have an Allen wrench, you can still use it. Just be a little more careful. And it's ideal that you go out and buy a set of Allen wrench. It's pretty cheap and just tighten it. Next, you will notice there are 2 screws in the front and 2 screws on the side. These parts control how tight the middle bar is. If you find that middle bar start wiggling, that means it's too loose. All you have to do is take your finger and tighten those screws a little bit and you're all set. The last thing is the handlebar have a screw also. You do not want to tighten that too much because you want to be able to slide the handlebar up and down. After you follow all these steps, your ArborPress should be calibrated and ready to go. As a reminder, it's important that you place the machine close to your body because when you press, you're using your body weight instead of just your arm. So it's even better if you have a shorter table at home. That way you can just lean into the machine. The last and very important thing is both of your hands should always be doing something. So if you're pressing down and one of your hands is not doing something, that is a red flag. Now place your left hand on the ArborPress while you're leaning into the handlebar with your right hand. The goal here is using your body weight and not just your forearm. Start with 80% of your body weight. You would press down, relax, and repeat it 3 times, and your product should be repressed. When you are applying pressure to the arbor press, always be in control. Hopefully this helps. Thank you.
Even though I know we're not going to be arbor press operators, okay, I thought it was a nice way that you can see how things go together and even get a feel for or a look at what those fits might be, because those are going to be things that are going to be important as we're beginning this project. So I am going to close out that. If you want to review that again, go right ahead. The details for the arbor press. Some of you had gotten this handout the last time we were together, but it's a PDF right here. And this is a, if you would, this is basically a 1-page PDF of all the parts. And we see like a put together arbor press. Again, I know that especially that photo, it's kind of far away, it's small. We have a couple versions of the arbor press, you know, available here at WCTC. And then also that video, I think, was a nice showing of many of the parts that we see on here. Okay, so we will be referencing this as we go along. So I am going to go back into my learning plan here. And where we're going to start today is going to be on the tolerances and fits handout. Okay, tolerances and fits handout. So if you wanted to, you know, have access to that, this is going to kind of be, if you would, my lecture today, kind of the introduction to, and then it'll be the application for the second practice problems you have, which are practice problems, fits, or tolerances and fits that this is gonna apply to. So I'm going to go underneath my camera. And I'm going to kind of go through this handout. Now, again, some of this information, I believe you've caught briefly at different places, but I don't think in our program up until now that we have actually like applied it. Okay, you've been probably aware of it, but this is going to be good, like I think review, but then also being able to turn around and apply it in a practical way on our assembly. So as we start on this handout, I didn't make a PowerPoint presentation for it because again, I'm going to kind of hit the highlights here and then do some of the examples. It would be a lot of back and forth anyway. So at the beginning here, they talk about precision and tolerances. Precision is basically going to be how accurate something has to be in order for it to function properly, okay? Once we identify the amount of precision, the higher the precision, so the closer the tolerance has to be, and the more repeatable of the small tolerance, the higher the cost, okay? The higher the cost. And that really is going to let us know that if we need something really precise, we're going to have a small range of tolerance that we apply on our drawings, okay? So if we are able to, and as the designer, as the engineer on a project, we are responsible for optimizing the range of tolerance so that the parts will always function, but also be manufacturable at a reasonable cost, okay? At a reasonable cost. So that's what they're talking about up here. And then they formally identify, or they formally define, if you would, what a tolerance is. It's the allowable amount of variation that is given on a size that'll provide the appropriate size so that it will actually achieve the final design function that we're intending it to do, okay? It ensures interchangeability. So if this part, for instance, per our drawing is made, whether it's in our current shop or at another shop, you know, down the road or in another state or in another country, we should be able to bring parts from any one of those places. And if they're made to the print, they're all going to function as intended. So we need to have the tolerances on there. I also want to preface this with, if you recall from GD&T, we did talk about how there's a lot of variation that comes into any one process, and that reality is we can't make any two parts exactly the same, okay? And that's why we need to identify a range for which we can accept, and those are the tolerances that we're going to be applying to our designs, okay? So again, the smaller the tolerance, the more expensive. That's kind of like your target, like how wide or how narrow is the target that I'm trying to hit. The more narrow that is, the higher the cost. That means small tolerance. The larger or the wider the target, large tolerance, it's not going to cost as much. Okay, so ideally, we want to give as much tolerance as possible, but our design is still going to you know, function and work the way it's supposed to. Now, down here, there's a nice little illustration. And what they have is a very simple part, okay? And on here, we have a couple different tolerance levels. Now, whenever we have a tolerance, a dimension called out, every one of those dimensions on that drawing has a tolerance, okay? If the tolerance is identified, you'll notice here we have tolerances identified in terms of limit dimensions, where we're given what is the highest value, what is the lowest value, gives me the range, right? The high and the low range. But if we have a dimension, well, and then I should say, then we're making our parts within that range or at one of those extreme values. Now, if our part has a dimension like 3.75, that doesn't mean we have to make it at 3.75. What that means is if there's not a tolerance specifically specified or limits like we see on the other dimensions, those default to what would be a title block tolerance on the drawing. Okay, so when you specify dimensions on a drawing, you're also specifying assumed tolerances based on the title block. So we don't want to say, oh, I like the way 2 decimal places look on this drawing. It looks nice and neat if they're all the same, because they're all going to default to the same tolerance. And chances are there are things on that part that may be able to have a larger or a smaller tolerance or need to function. So it is important that you remember that every single dimension on the drawing has a tolerance. And if it's not specifically specified, it defaults to the title block. Now, that is why it's important on a company level, WCTC, we have our own title block tolerances. Know what your title block tolerances are. As a designer, you can never change those. That is not an option, because once people know and identify a company's tolerances, their standard tolerances, nobody looks at the title block anymore. And if you all of a sudden do a switcheroo and you change the title block because you didn't want to put a tolerance on all the 2-place decimals, no one's going to like that. Okay. You're going to have a lot of parts that aren't going to be made to print. So it's really important that you never change a title block. What it is, it is. And then you just have to, you know, work with it in that sense. Okay. So any questions here so far? Great. It's all easy. It's all stuff you've already known, right? Right. Okay. On the next page here, they talk about the different types of tolerances that we have. Okay. And these are categories of tolerances. So the first one is a limit tolerance. A limit tolerance is going to specify that range for which we want our feature or our part to be within. What's nice about specifying limits is nobody in their head has to figure out plus or minus 5 thousandths or something on a nominal value. It's the safest one. So especially when you have critical dimensions, it's best practice to do limits, quite honestly. Okay, best practice to do limits. All right. Bilateral tolerance is when our variation is on both sides of what we would call the nominal value. Okay, so for this case, we have 1.75. That would be what we call our nominal value. In the English system, our nominal value, we want to use what we call a basic size. A basic size is going to be on one of those nice fractional increments. Okay, those numbers that mean something to us. Okay, so you'll notice here 1.75. They have a bilateral dimension, meaning they're allowing plus 3 thousandths minus 2 thousandths. So this is one of those cases where we would have to kind of do that math in our head, or whoever's making the part. So the highest value here would be 1.753, right? And the lowest value would be 1.748. So the limits, if you would be those high and low values that we see there, but the dimension is given as a bilateral with some tolerance on one side and some on the other, okay? Another version of a bilateral tolerance will be an evenly distributed bilateral tolerance. And in this case, it's plus or minus 2 thousandths, okay? Okay. So bilateral tolerance, we've got something on either side of that nominal value. Unilateral, on the other hand, means that we're only going to have tolerance on one side. It might be plus something minus 0 or plus 0 minus something. And that we see examples of in these cases right here. Why would we do that? Well, a lot of times you want to preserve that basic size, okay? People can relate to 1.375. If you put a basic size as a 1.374 plus or minus 2 thousandths, they might be like, why didn't you just put it to 1.75, right? Because that's what people relate to, especially in manufacturing and the machining industry. tooling is made to fractional sizes when it's English, so it just kind of makes sense, okay? So you always want to think of the people who are going to be making it. And then it identifies the general tolerances, which are our title block tolerances we already discussed. So if there isn't a tolerance specifically on a drawing, it always defaults to the tolerance in the title block. Okay, questions there? Some nomenclature or a fancy word for vocabulary, nominal size. Nominal size is going to be that designation used for, you know, what is the basic size? Basic size and nominal size are about the same. And basically all that is it's what's the target number that you have. The nominal size can be really any number, but a basic size is going to be one that is typical to the units of measure that you're working with. So in the English system, it's going to be those fractional values. In the metric system, it's going to be to the whole millimeter, okay? Actual size, this is going to be what it's actually made to. So for instance, maybe parts were made to your drawing. There's a basket of them, and you go and you grab one of those parts out of the basket and you measure it up. Well, what is the actual size? And hopefully it compares back to being within the range identified on the drawing within the tolerance. Now, a fit is going to be the general term used to signify how loose or tight something is. We're going to be talking about fits in detail in just a little bit, okay? And this is when we have parts that are mating together or are going to be working or functioning, you know, reference to each other. Allowance. Allowance is going to be what we say the minimum amount of clearance. It's intentional that we design when two parts are fit together. The tolerance, as we know, is going to be the total permissible variation that we're going to allow, where things are still going to work. And then from GD&T, you guys remember this, maximum material condition and least material condition, okay? You're like, oh, got enough of that back then. But just as a reminder, if we have external features like a shaft, maximum material condition is always going to be the largest side. So SH just means shaft or external feature, okay? A lot of times we talk shaft and hole because we're going to find that our charts are set up and worded that way, but it can be a ram that's going to go into a recess, okay, where the ram would be like an external feature, a shaft, and the recess would be the internal feature or the hole. So they don't have to be cylindrical. They can be non-cylindrical features of size. So MMC for an external shaft is the largest. The LMC for a shaft or an external feature of size is going to be the smallest size. Opposite for internal features like holes, right? MMC is going to be that smallest hole size, and the LMC is going to be the largest. Okay. All right. So as we look here at the hole designation, you're going to notice that the smallest size is on top. The smallest size is on top. The larger is on the bottom. Now, this used to be a thing, and it's still good practice if you think of it, but usually in softwares like AutoCAD and AutoCAD and in SolidWorks, when you set up the tolerance that you want, they usually just do plus and minus, plus on top, minus on the bottom. The reason we see well, I'm going to ask you, why do you think the 1.125 is on the top here and the 1.127 on the hole size is on the bottom? Any ideas? Tyler.
You kind of have a rigid but maximum material condition on top, which is, from what you all told us, it's better to 9 times out of 10. 9 times out of 10, it's better to be at max material condition than least material condition in DD&T.
Yeah, we use that a lot. You know, that's a good thought, but it's not, I'm sorry, it's not the reason that it's there. It's a manufacturing reason. It's a manufacturing reason. I know I've said this before, but it's just depends. Anybody have a manufacturing reason? So if I was going to make that hole, what's the size drill? I don't know. Hopefully there's a 1 1/8.
It's a drill bit.
It's a drill bit size, right? So when you make that part, and say over time, maybe I make 120 of these, and that drill starts to get dull. What happens to the hole size?
It's smaller.
It does not. When you have a dull drill, it actually increases the size of the hole. It's always kind of that opposite of what we think. The drill physically is getting smaller, but the chips that we're generating are actually getting more coarse and they're actually boring out that hole at the same time. So the natural effect of a hole when the drill dulls is that the hole is going to get larger. Okay. That's why we see that. Now, am I gonna look at that on your hole sizes and say, you know, you should have that there? No, but you may see that in places. And in this case, that's why it is on top. Most often the CAD software is if I have a plus or minus, it's going to put the largest value on the top, the smallest value on the bottom, whether it's an internal or external feature. But you may see this in maybe older drawings or people who maybe, you know, have been designing for a while because that's a thing. Okay. Thinking manufacturing wise, but whether it's on the top or the bottom, highest and lowest, the range is still the same. Okay. So that's that. And then you're going to notice over here on the right-hand side, then we've got the high and the low values here. For an external feature, the high is always on top and the low is on the bottom. As we look, allowance, which is really considered minimum clearance. Okay, allowance, minimum clearance. To calculate that is going to be, we like to say, one of our worst case scenarios. So minimum clearance means this is the minimum amount of space I'm going to have between these two parts. Okay. So I'm going to take the MMC size of the hole, the smallest hole, minus the MMC size of the shaft, the largest shaft. So in a sense, that's kind of the worst case scenario, fitting something together, right? So in the case up here, I'm going to take the MMC size of my hole, 1.125, 1/8, minus the MMC size of the shaft, 1.124. And I'm going to notice that minimally, I've got a positive 1/1000. Okay, so when I subtract these two numbers, hole minus shaft, I end up with a positive value. Positive means clearance. There is physical space between those two. Okay. Maximum clearance. Okay, so how much am I going to, you know, from that minimum, how much more am I going to get based on the range? So this is going to be my LMC hole, largest hole size, minus the LMC shaft, the smallest shaft. And you're going to notice here that my number, when I take those values, okay, and I subtract them, I end up with a positive 6/1000. Again, a clearance of 6/1000. So the worst case scenario, I'm within 1. Worst case, and then the maximum amount of clearance is going to be that I'm going to have up to 6. And then anywhere in between, right, is going to be how they're going to fit. So the fit here is always what we call a clearance fit, because there's always going to be space. Okay, so they'll always go together real nice. Not going to be hard to put them together at all. Okay. Let's look at the example that we have here. So this is an example 9-1. And what we want to do is based on the two parts that we have here, and we're going to just kind of go through because they have the values down here. I just want to make sure that we understand them and where the numbers are coming from. But we've got a hole, 1 1/4, and we've got a little bit less on a shaft, 1 1/4, if you would, nominal size. But we've got our limits for each one of these. And what we want to find is what is the nominal size? What is the tolerance on the shaft, on the hole? What is the allowance, minimum clearance, and the maximum amount of clearance? Okay. So first of all, as we look here, as we look at the numbers between the two, what is the nominal size of the hole? And really the nominal size of the assembly. What would we say that is?
1.25
inches. 1.25 inches, exactly. Yes, 1.25 inches, 1.25. Now we have limits that are, you know, off of that, but that's the basic size of this assembly. Okay, basic size of this assembly. So nominal size is 1 1/4. Now, the next thing they want to know is what is the tolerance on the shaft? So the tolerance on the shaft is the amount of variation that we are allowing on this feature. So tolerance is simply going to be the difference between the highest and the lowest value. So we would take the 1.2496 minus the 1.2493. Looks like it's 10/1000ths of an inch, or no? Oh, 3/1000ths of an, or 3/10,000ths of an inch. So we would subtract those, and here we have 3/10,000ths, 0.0003. Now, I don't know. What do you think? Is that a small or a large tolerance?
That's small.
It's a pretty small tolerance. Okay, pretty small tolerance. You would have to, you know, have a nice, capable machine, probably newer, or it might take you longer to get to this tolerance. It's a small target that we're trying to hit, okay? So that's the tolerance on the shaft. Tolerance on the hole is doing that very same thing. We're going to subtract the highest limit minus the lowest limit, and here we get 4 10,000, so 0.0004, another small tolerance, right? Small tolerance, okay? Now, you as the designer would be, justifying that if you would, like that's critical. When you have bearing fits, yeah, you're gonna have 4 or 5 decimal places that you're gonna be dealing with, okay? But if you have an arbor press, part here that we've got to fit in, probably don't want to be within tenths of thousands, especially when we saw the operation and we saw, you get a little bit of wiggle room and things like that. So you got to look at the final function and how critical it has to be. So, I mean, those are not bad tolerances, but you want to make sure that it's appropriate for the function of that assembly. So now allowance here, I just have a little note, that's your minimum clearance. So we're going to take that MMC size of the hole. It's that same equation that we got back here. Here's that standard equation, MMC size of the hole minus the MMC size of the shaft. So we're going to go back up here, and as we look, MMC size of the hole, this is going to be my smallest hole size. That's that top number in this case. MMC size of my shaft, largest shaft, MMC size is going to be the top one here. So I'm going to take 1 1/4 minus 1.2496, okay? And you'll notice that our allowance is a positive 4/10 of a thousand, okay? Remember, the thousandths place is right here. So now that extra decimal, that's 4/10 of a thousand, so the 10,000ths place, okay? So the positive value here equals clearance. Now, in this case, 4 10,000ths, I don't know, it's going to go together real easily because we have to make sure that however, long this is, we don't know how long that shaft is. As long as it's nice and straight over its entire length, we're good to go, right? But, we'll see. Maximum clearance. Okay, now we're going to take the largest hole minus the smallest shaft. Okay, and to do that, we're going to take the bottom numbers then. So the LMC is down here and LMC is down here. We're going to subtract those two, hole minus shaft. And here we get another positive number. So again, we have clearance and we have 0.0011. Okay. So that's the maximum amount of clearance. So this is the range of clearance that we're going to have. Okay. All right. Questions on that? I'm just going to ask, in your tech drafting class, did you guys do this kind of stuff and look at the charts and things like that, or not too much? We did a little bit in GD&T, but we looked more at the GD&T tolerances themselves. Okay. All right. Well, since that's the case, let's do this. Grab out a piece of paper. And this one, I'm going to give you a couple minutes. This is at the bottom of page 9-5. And using the values that you see here, let's determine nominal size, tolerance on the shaft, and I'm going to zoom in so that you can see these things, okay? Tolerance on the shaft, tolerance on the hole, allowance, and maximum clearance, okay? So go ahead and just kind of write them out based on the numbers here. This is for your eyes only. You won't be handing this in, but it's just good practice to make sure that we understand the values that we see. And give it an attempt. And if you're not exactly sure, that's okay. We'll go over it in a couple minutes here. I want to get you the opportunity to write down your thoughts, okay? Okay. Even if you're not completely done, let's start looking at the values here. So I just wrote down the values for the hole in the shaft in terms of the range of the tolerance that we have, okay? So as we look at these numbers, nominal size for this assembly, what are you thinking? 1 1/4, yeah. I mean, these over here aren't super, I mean, but it's based on a 1 1/4 on our size, or on our hole size. So 1.25 would be the nominal size that we would be looking at for, our assembly, okay? Shaft tolerance, okay? Shaft tolerance is going to be the difference between the high and the low value here that we're allowing that feature to vary. So that means our shaft tolerance is going to be the 1.238 minus 1.222. And what do we have a value? What do we have for a value there? Right, hard. 0.016. Okay. Trying to make it darker so that those who are virtual can see. 0.016, 16 thousandths. Okay. Then we're going to do that very same thing for the hole. So here we're going to take that 1.250 minus, oh, I should have done it. No, I did it the wrong way because they have the smallest size on top. I'm going to put the 1.266. It's really just finding the difference minus 1.250. And looks like we have 16 thousandths there as well, right? Okay. 0.016. Okay. Good. Any questions so far? So the tolerance is the difference between the high and the low. There won't be a positive or negative value for the tolerance because it truly is how wide or how narrow is the target that we're trying to hit. And in this case, that's the target, right? 16 thousandths is what we want to be within. Compared to the example that we just looked at, this is a much larger tolerance, right? If you would, more reasonable for like kind of basic milling machine, machine shop type of stuff, okay? Or even lathe work, okay? Good. Now, as we look at the fit between them, we want to find out what is the allowance? What is the minimum amount of clearance? To calculate that, we're going to take the MMC size of the hole, smallest hole, minus the MMC size of the shaft, largest shaft. So if we go up here, the MMC sizes for each of these are the top values, right? So we're going to take 1.250 minus 1.238. So this is going to be equal 1.250 minus 1.238. And what do we get for our allowance? I'm just going to put allow. 12 thousandths, 0.012. Okay, agreed. So it's the difference between these two. Yep, we just subtract those and we get 12 thousandths. So that means that, and it's a positive value. So positive equals clearance. Okay, positive equals clearance. If we would have a negative value, that would mean that space is occupying, or space from each one is trying to occupy the same place. Okay. And we don't have that. We have clearance. So 12 thousandths is going to be the minimum amount of clearance. And then we're going to do the maximum amount of clearance. This is going to be our LMC size of the hole, the largest hole, minus the smallest shaft, which for our range here are going to be the bottom numbers here. So this is going to be 1.266 minus 1.222. And let's see, this is going to equal, it's going to be a larger number, right? Max clearance, what do we get?
44 thousandths.
Yep. So it'd be 44 thousandths, 0.044. Okay. Almost feels like a mile compared to the last problem, right? Okay. So very different, but that doesn't mean it's right or wrong. It doesn't mean it's bad or good. There's really not judgment on the number. It just has to be appropriate for the final function. And if it's going to function the way that it's intended to, then we're good. Okay. And we want to maximize those tolerances and make them as large as possible. Okay. So you will be doing work like this, similar to that for like your practice problems. There's going to be some things to fill in for that. Okay. Just so that you're aware. So I want to make sure that you know how to do that. Okay. Let us turn the page and let's start talking about fits. Okay. Fits between mating parts. So our ASME standard or ANSI standard, the Y14.5, designates different types of standard fits that we have, okay? There are 4 general types of fits. There's clearance, interference, and then two that are kind of like in between, transitional fit and line fit, okay, or sometimes referred to as locational, okay? So clearance, we were just looking at clearance fits. It's when there's always space between the features as they're being put together. And then there would be a minimum clearance, but there's still space, and there's going to be a maximum clearance, okay? Interference is when there is going to be the two shapes trying to occupy the same space. And it has exactly that. There's going to be interference, and that is at all levels. So when we try to figure out what is the minimum amount of interference and what's the maximum amount of interference, we're always going to get a negative number using those allowance calculations that we have. And that negative means that we are in an interference state. Now, again, no judgment. It's appropriate for some things, okay? We're going to find out, and we're actually going to be applying a press fit for one of the parts in our assembly, okay? And it's intentional. So it's, again, not bad. It's just that it's the type of fit that's going to be maybe pressed or even heated up and cooled down to fit together, okay? And then the other two are in between each one. So there's a transitional fit where sometimes you're like on that border where you're gonna have a little bit of a clearance and you're gonna have a little bit of an interference, okay? And then we also have line fit. And this again is where you're gonna have a little bit of clearance, a little bit of interference, but they're like locational. So things like dowel pins are gonna be this type of a fit, okay? All right, so in general, those are the fits. Now, basic hole and basic shaft system. Basic hole system is going to be how we use our charts, and we're going to be working these fit problems 95% of the time, okay? And what all that means is the basic size is on the hole for the reason we talked about earlier, that when we make the hole, it's going to be to a drill size, okay? And we're going to pull that off the shelf. We're not going to make a special drill each and every time. We want to use something that's standard tooling. So hole system, we're going to have the nominal size on our hole, okay? And then we're going to be applying then the allowances then to the shaft. Now, if you have a basic shaft system you're working with, that means that the nominal size is now on the shaft instead of on the hole. This can sometimes be where when we're getting in a drill rod, for instance, and we're going to be using it as a standard size, and the shaft is already made and ground to the size that we need it to be, okay? Then we're going to make the hole to fit the shaft, and the shaft is already a nominal size, okay? Doesn't happen as often. They're a little bit more specialized types of applications, but they're out there. But it just kind of, that's the only difference between them. So the basic hole system is what we're going to be applying and how we use our charts, okay? Now, the charts. There are standard fits. As we had said, there's 4 classifications of fits: clearance, interference, transitional, and locational or line fits. In each one of those types of fits, we're going to have classes, okay? So for instance, RC means running or sliding clearance fits. Running clearance fits is what it's usually referred to. RC fits. LC is going to be those locational clearance. LT is going to be transitional clearance or interference. LN is locational interference. Those are like the dowel pin holes, like I said. And then FN is going to be a force or shrink fits, okay? Now, as we kind of, this one's kind of the in-between, but as we look up here, these are always clearance, okay? And it just depends on the degree of clearance that we want. We're going to pick what we call the class in each one of those. Down here, these are totally interference. And again, how much interference we get is going to depend on the application, but how much the class is going to be dependent on how much interference. So we're going to look first at running clearance fits. Okay, running clearance fits. Running clearance fits have 9 classes within them. Starting with RC1, this is going to be the closest sliding fit. So it's going to be, not much clearance between them. Okay, they're going to be closer. So if I move them relative to one another, I'm not going to feel much difference. Okay, not much gap or slop. As I move through up to an RC8 and an RC9, now I've got, if you would, sloppy parts. Okay, sometimes if you look at a very simple axle on a toy dump truck. That's going to be like an RC8 or an RC9 fit. It's not going to be super critical. It's not going to be running down the highway at high speeds. Okay. So you want to make the fit appropriate for the application. Okay. And then there's, you know, also then there's the range in between here. Okay. When we have charts, okay, and we look at, for instance, and we'll be looking at these in a little bit, and that's the second handout that's here. Here we have the running clearance fits, RC1, RC2, RC3. And so once you determine what the appropriate fit is, now you're going to, you know, go to the appropriate column. Now, to know if it's an appropriate fit or not, the charts that we have here have better descriptions of each one of the fits. Now, you might say, well, RC3 and RC4 kind of sound pretty similar. Yeah, they do. And it's your call as the designer to determine which one you feel is best. So for instance, when you guys pick fits for the Arbor Press, as long as they're reasonable, okay? So like I said, as long as, let's say you're trying to decide, some people are picking 3s, some people are picking 4s, some people are picking 5s, I call everyone correct. As long as you're not picking a 1 and a 9, all right, at the end of the spectrums where it was like, the description is kind of in between, you know, you should be picking something closer to the middle. That's where you look. So if you're comparing to somebody else and asking, what is the fit that you chose? As long as you're within 1 or 2 or in the right range, you can call both of you good, because I think there's a case, you know, to be made. So does that make sense to everybody? Okay. Because again, when you read some of these descriptions, you know, precise running fits, close running fits, and then you read, you know, what the description is, it's kind of splitting hairs, especially when you're going from one class to the next. Okay. So as long as you've made a reasonable judgment, and it's about where I would pick too, and I'm not saying I'm completely right either, because somebody might, you know, with experience too, pick something a little bit different. That's okay. All right. So the descriptions are up here. I'm not going to read every one of these, but know that 1 is the most precise in the running clearance fits, and 9 is going to be the sloppiest, if you would. Okay. All right. As we look down here, when we want to figure out those minimum clearances or maximum clearances, we're using that same equation, MMC of the hole minus MMC of the shaft. Now, again, these don't have to be cylindrical features. We're going to find on the Arbor Press, we're going to be applying it to the ram and the recess in the frame. Okay, those are non-cylindrical features, but the cylindrical side, or the external feature would go on the shaft side column, and then the internal feature will go on the hole size. Okay, you just don't put a diameter symbol in front of the dimension. That's it. Okay. All right. This is the difference between an RC1 and an RC9 with the same nominal value. Minimum clearance on an RC1 is 8/10,000ths. Minimum clearance on an RC9 is 14 thousandths. Okay, so again, running that you know, high and that low value in the classes. Okay. All right. Okay, locational fits. Locational fits, as we said earlier, they are going to reflect the transitional clearance fits or locational clearance fits. So this is when we have line-to-line contact and we want them to be smooth running between them, but super accurate. So, so things like pins that we want to maybe rotate, but we want to hold location, but it's going to freely move, are going to be applications like this. So again, you're going to notice that as we are more accurate, we're holding it out to 4 and maybe even sometimes 5 decimal places to adhere to that tolerance level. Okay. As we look down here, as we look at the difference between the two values here we have maximum clearance is only 1/1000th of an inch, and the minimum clearance is actually at 0. Okay, so this is going to be locational clearance fit. So line-to-line contact is what this would be considered, where there's no clearance, but they're the same size going in and out, 1.25, 1.25. And then here we've got just a little bit of clearance. So very accurate tolerances here. Okay. All right. Transitional clearance or interference. Okay. Here again, we're holding to, it looks like 4 decimal places here. As we look at the maximum clearance, this goes from 10,000s or 0.0013. And then you're going to notice here that we end up with a negative 0.3 of a thousandths. Now, the positive value here was a little bit of clearance, and down here, a little bit of interference. Okay. This is probably tapping 0.3 Probably, I mean, I don't even know if you need an arbor press for that. You probably could tap that in with a hammer or a mallet, I think, depending on the material. Okay. But there is interference there. So they're trying to occupy the same space, if you would. Okay. All right. And then this is locational interference. So again, between the locational clearance, the transitional clearance and interference, and the locational interference, all very close. They're all very, very close. So small numbers again. Line-to-line contact when we have our maximum clearance, if you would. So really not clearance, it's line-to-line contact. And then here, our interference is 11/10,000ths or 0.0011. Okay. And then the very last one is a force or a shrink fit. This is when we're sliding into the category of you're gonna have to press this together with a machine. Okay. Even when we've got the FN1. So the force fits, FN fits are going to go from 1 to 4. Okay. 4 meaning that even at times you might not only have to press it together with a press with a machine, but you probably will even have to heat one up and cool the other one so that you can get them to fit together and then let them come to room temperature to stay and actually be stationary to one another. So light drive fits, that's going to be our FN fit. So there won't be quite as much interference, but then as we get to the FN4, large amounts of interference. So if we look down here, again, you're going to notice that this is an FN1 fit. The numbers that we see here are negative. Hold on. Let's try to zoom in and focus. Negative 0.0003, so 0.3/10,000ths. That's going to be our minimum interference. Our maximum interference is going to be 0.0013. Notice the negative for each one of those because, again, that means that there's an interference fit. Both parts are, we're still using the hole minus the shaft. So the hole is smaller in every case than what the shaft is, okay, physically. All right, now, how do we use the charts? That's what we're going to practice on the next pages, okay? So there's a couple here that we're going to be doing. I think we're going to do two of them on the next 2 pages because they're the basic hole system. This is what you're going to be applying for your project. And like I said, this is 95% of the applications that you will see ever, okay? And then there is a couple that are basic shaft system, but I'm not going to go over those because again, we're not going to apply them, but know that it's there if in the event you need to use it, okay? So let's look at this very first one. And this is going to be similar to, again, some of the questions you're going to be asked in the practice problems for the tolerances and fits. You're going to be using and looking at the parts in the arbor press and picking what the appropriate fit is, and then what the ranges of size and stuff are going to be for each. So as we look here, a design requires that 2 mating parts have a nominal size of 3/4 of an inch or 0.75. The shaft is to run with a moderate speed, but fairly heavy journal pressure. The class of fit that was chosen is an RC6. Now, again, whether it's an RC6, an RC5, an RC7, let's not get caught up in that. As long as you're clustered close to that, okay, would be a reasonable value. So determine the size limits of the 2 mating parts, okay? Now, this is where we're going to get out the charts. Now, I realize you have them in PDF form, so if you want to, if we go back to our module, this is going to be the Module 2 fits charts PDF, okay? All right. And I have mine printed out here. So what we want to do is we want to find the RC fit. That was kind of given to us already. So I'm on the first page of that handout. These are the running clearance fits. So we have our RC 1 through 4. I'm going to turn the page and we are going to find the RC6. This is the column for the RC6. Okay. Now, as we use this chart, now these charts are standard. So if you go to the Machinery's Handbook, these are all published there, okay? This is just another version of, or if you look online and you look for clearance or running clearance fit charts, you're going to find them, okay? The only thing about Google searching that, just verify you've got a good source, okay? That's the only thing. You should. I can't imagine that this would be much different. Now, how to use this chart? First thing we're going to do is down the left column, we're going to find the size range. So our nominal size is what we're looking for. Our nominal size in our example is 3/4 of an inch, 0.75. So we're going to find where it falls. So it's going to fall right here between 0.71 and 1.19, okay? Between those two. Later, okay? So I'm going to highlight that right there, okay? Now what we're going to do is I'm going to kind of scooch this down a little bit. We are going to go over to the RC6 columns, okay? The RC6 columns, those are right here, okay? Now, the first column is limits of clearance, okay? So this is a clearance fit, so we're going to have maximum, minimum clearance. So they're giving us some numbers there. Let's not worry about that just yet, all right? But then you're going to notice that there is a hole number and a shaft number or column, okay? Don't worry so much about the H9 and the E8. That's not going to come into play. We're worried about these numbers right in here in these two columns, okay? Now, how the columns work. The column numbers are to the 1,000th of an inch, okay? So instead of putting in 0.0002, they're putting in 2, okay? And what you do is you move the decimal place 1, 2, 3 to the left. That's what you do. So if you would, it's to the times 10 to the negative 3, okay? So it's to the 1,000th of an inch, all right? So that means we're going to add 2 thousandths to the nominal size on the whole, okay, for its maximum size. And then we're going to subtract 0 for the minimum size hole. Well, that sounds familiar. Remember, that's going to be the size of the drill, the nominal size in our hole size. Then on the shaft, we're going to take that same 0.75, but we're going to subtract 0.0016. So again, 1, 2, 3 to the left. So that's going to be 0.0016. And then we're going to also subtract for the lowest limit on the shaft, 0.0028. Okay, 0.0028. So I know they have it written out there, but I think it's worth kind of showing you how this works. Okay, and showing the numbers. So our nominal size, so I'm going to do the whole first. Our nominal size is a diameter of 0.750, okay? I am going to, again, I'm looking at the whole column here, okay? I'm going to add 0.002, and I'm going to subtract 0.000, okay? So now the limits created by adding 2,000, subtracting 0, this is going to be 0.752 over 0.750. And again, if you want to put the 0.750 on top, that's fine. It's just that, like I said, CAD systems are just going to do the max on the top, the min on the bottom. Okay. So you can leave it just like this. So this is the limits of the hole size that you would put on your drawing. Okay. Based on the fit that you picked and the class that lined up with your fit. Does that make sense to everybody? Okay. So it's doing the work for you. You don't have to randomly be like, I want to add a 0.5 thousandths here or subtract there. It's got it here for you. Okay. Now, shaft. Okay. The shaft has the same nominal size, 0.750. Okay. But the last column here, the shaft column, I'm going to subtract, right, 0.0016. For the top, and then I'm going to subtract 0.0028 for the bottom. Okay. So now those numbers, if I do the subtraction there, I don't know what the number is. Somebody's got to plug it in their calculator. Anybody have it yet? I'll watch the chat box. So you guys are pretty fast.
0.7484 on top.
Okay.
And 0.7472.
7.2 on the bottom. That looks reasonable to me. Okay. And now on my drawing for the shaft where it's going to fit with this hole, those are the limits of size that I'm going to put on my drawing. Those are my tolerances, okay? Because again, I picked the fit based on the final function that I want. I have a nominal size and I applied the limits appropriately. Now, let's look back to this column right here. These are the limits of clearance, okay? So all that's doing is it's gonna find the maximum clearance and the minimum clearance. So as we know, minimum clearance is that allowance equation. That's going to be MMC of the hole minus the MMC of the shaft, okay? So the MMC of the hole, okay, is going to be the smallest hole size, right? Maybe MMC. So that's going to be 0.750 minus the MMC of the shaft. This is going to be the MMC of the shaft, the largest size, right? So that's going to be minus 0.7484. So the minimum clearance, what is my number here? It's 16 thousandths. Yeah. And if I look up here, that's the minimum clearance right there, 1.6. Okay, and remember, thousandth of an inch, 1, 2, 3 to the left. Okay. Maximum clearance. That's going to be the LMC of the hole minus the LMC of the shaft. Okay. So if I go back up here, my top number here is going to be my LMC and my bottom LMC, right? Largest hole, smallest shaft. So I'm going to take 0.752 minus 0.7472. Okay. And that number should be 0.048. Just verify that. Oh, yes. And 0.00. Yes, we moved it 3 places, 0.0016, because it's 16123. Yep, 0.0048. Thank you. Because it's here, 1, 2, 3, and it's 4.8 here. Thank you. Yep, zeros. I'm gonna add the zeros. Because this is a 0 here, right? Then we would subtract. Any questions about using the chart for that example? Okay. All right. So once you determine the appropriate fit, now you just use your nominal sizes and use the chart in thousandth of an inch. Okay. Let's turn the page. We're going to do one more example. This is example 9.3. Same basic hole system, but this time we're going to apply an FN fit. This is going to be a press fit, okay? So the nominal size here is 1/4 of an inch, and we want to determine the size limits of the 2 mating parts, okay? 2 mating parts. So in this case, I'm going to turn this over. We are going to, we've got a nominal size, and that's equal to a diameter of 1.25. And our fit is picked for us, and that's an FN4. Okay, FN4. So on our charts, we're going to look for the FN fits. So this was my RC fits were first. Then I had running clearance fits or LC fits. I think these are LT fits. Should be the last ones here. Yeah, the last page. We've got the FN fits, okay? 1 through 5. Directly above on each one of these charts, you're going to notice that there's a description for each type, okay? So again, you want to best guess, if you would, what the description is to line up with your application. So we have an FN4, and it's a 1 1/4 inch nominal size. So our FN4 is this column right here. And we're going to go over to the right-hand side here, and we have to find our range. So we're 1 1/4, which is the very bottom right here, actually. Okay. And then we're going to go over to the FN4 column, which means that we're working with these 3 columns right here. This is the limits of interference, hole, and shaft. Okay, hole and shaft. So same process that we do here. The numbers are in 1,000th of an inch. Okay. So we are going to use the values that we see. So for the hole, you do that first, okay? So the hole is going to be a diameter of 1.25. That's its nominal size. And this is the whole column. Okay, it's the middle one of these three. I'm going to add 1,000. So I'm going to take this 1, 2, 3. So 2 zeros and a 1. And then I'm going to minus 0. So the limits of my hole are going to be 1.251 to 1.250. Okay, the nominal size is on the hole. Then I'm going to do that same thing for the shaft. I have a diameter of 1.25, and for the shaft, which is the third column here, I'm going to add 0.0031, and I'm going to subtract 0.0025. Now I need your help with the sizes here. This one, I think I can add 0.2531 is the top, right? But the bottom, what do I get? Oh, this is an add. This is an add. I'm sorry. This is a plus and a plus. Make sure you have the right sign. So this is a plus. I think I can do that one too. 0.2525, right? Okay. So these are the limits then. These are the numbers when I'm on my drawing on my shaft that's going to fit with that hole. These are the values that I'm going to use, whether that's applying a tolerance or the limits as we see them here. I would always go with limits. If I've already calculated them, why not put the limits on? And then it's easier for somebody else to be able to go between. Okay. Any questions on applying the values? We could calculate, you guys want to calculate the limits of interference, but it's the same as the allowances that we saw before for the, it is the same. Yeah, it's the difference between, just like we did before. So let's look at where we're at on a handout. I think that brings us to the end of our handout. It does. It does. Okay. So the rest of the pages you are not responsible for. Okay. So let's take a peek at the assignment that this goes along with. Okay. The assignment that this goes along with. So if I go back to my module 2, and I'm going to go to the modules. Now, there's 2 sets of practice problems here. The first set of practice problems is dimensioning. This, as I said earlier, is a review for you. So bits and pieces along the way, whether it was tech drafting, GD&T, you've gotten this stuff. So this is going to be a review for you. So go ahead. You should have 2 attempts on this. I have it due next week, Friday, so that, you can, that's going to be the due date for it at the end of module 2. The one that refers to what we just looked at this evening is the practice problems, tolerances, and fits. Okay, so let's take a peek there and see what this looks like. Oops, you guys are going to go in and you're going to, that's right, cancel. I've got to go into student view. Sorry. When you guys click on it, you're going to see, if you would, the quiz. It's sort of a quiz. I'm not going to say it's a quiz. It's practice problems, but it's in quiz format. And what it's telling you here is that we are going to use, for the questions that are asked here, the parts from the Arbor Press. Okay, so we're going to start really looking at that. So we want to, I guess, resume. That's fine, because I think I went into it once. Can you guys go into it, right, as a normal quiz, if you would? Okay. Now, these are all essay questions, okay? All essay questions. And what we're going to do is it's going to identify 2 parts that you are going to determine the fits for. So there's 7 questions or 7 fits that I want you to figure out for the parts that we have on our Arbor Press, okay? So I'm going to pull our drawing underneath my camera here, so that we can kind of go back and forth, and that we're just going to briefly go over each one so that you can see the parts that I'm referring to and what they fit into, okay? Because this is also an exercise of, if you would, kind of getting to know the parts, and how they're going to fit together. So the first one I have here, we want to take the width of the RAM, part number 320, to fit in the rack recess on the frame 310. And you want to determine basic size or nominal size, basic, nominal, remember the same. What is the class of fit that you would pick? And then you're going to tell me what the limits on the rack recess are. That's going to be the hole. That's going to be the internal feature. And the limits of the rack width, which is going to be the shaft, if you would, column. So again, even though it says hole and shaft on our charts, think of it as external, internal, okay? So let's look at these two items. Go back underneath here. So the ram, okay? The ram is going to be the part that has the teeth on it, okay? All right, so it's right here. And if we look at the recess in the frame, so here's the frame. And if we look at here, this is a view looking down that part. There is two vertical lines right here and right here. And this is going to be the rack recess for it to fit into, okay? So this is going to fit the width of that ram, okay? Okay, so this dimension right here is the ram width. And this dimension is going to fit that value. Now, there are already values in there. They already have, for instance, 0.751, 0.7549, if you look closely. I know it's small. And then they have a nominal size up here of 0.75. It's not going to fit together all the time, because if this is on the high side and this is made to any one of those nominal values, there'll always be interference, okay? And that's not good. That rack needs to freely move up and down inside that recess. So in general, what type of a fit is this going to be? Is it going to be a clearance or an interference? Needs to be a clearance fit, okay? So what you are going to do is you are going to pick what that clearance fit is. So you are going to read the descriptions. You're going to find the beginning is the RC fits. You're going to read the descriptions here. Here are the first four, okay, and the first four, and then it has the next 5. And you're going to kind of determine, where do I think my fit for the rack and that recess falls? And then you're going to apply the appropriate tolerances, and you're going to document that here in the form of basic size, what's the class of fit that you picked, and then what are the limits of the rack recess on the frame, and then what are the limits of the rack width. When you make your drawings later on, you're going to reapply, that's where you're going to apply these tolerances. Tyler.
I have a question. So for the limits, sometimes they actually show some actual dimension limits on here. Do we use?
Nope. So you're going to pick the basic size. Okay. And even if on the drawing, you're right, they have limits there for the width of that recess on the frame, right? You're not using those. Okay. You're going to ignore that. You're going to ignore that. So what Tyler is asking is right here on the width of the rack recess, they already have 0.751 to 0.749. You are not using those. You are going to say that's a nominal size of a 3/4 inch. Okay. And this is a nominal size of a 3/4 inch. That's the width that's going to fit in there. Okay. And now you're going to pick a fit and you are going to document it here. Does that make sense to everybody? Okay. So you're going to pick an RC4, I don't know, RC5, RC3, whatever it is, and what you think is appropriate for this. And then you are going to document down in here, you're going to say limits of the rack recess are this. Remember, recess is a internal feature. There's material being taken away to create that. Okay. So that's going to be on the whole column in our charts. External features like the ram width, that's the shaft part. So again, they don't have to be, and like in this case, it's not cylindrical features, but we're going to apply the same thing, internal, external think. Okay. All right. Okay. So that's our first one. Here's the second one. This is the depth of the cut on the rack recess of the frame to accommodate the depth of the ram. So, as we look back underneath here, so this is the width, right? So if we look in this view, the depth of that cut is going to be this line right here, okay? And how it comes from the front, it's 1.186 and it comes back 0.434. The depth is this difference right here. Okay, it's that difference right there. I know it's kind of hard to see, but it's the line that they're dimensioning to right there. Okay. So that's how far back it's going to sit in here. So if we look at the RAM, the dimension for the depth is over on this side. It's going to be the 0.75 in this direction. So it's the same nominal value, 0.75. And you're going to now determine, all right, what is the appropriate fit? Now, again, even though it's the depth going in and out, do we need a clearance or an interference fit? Needs to be another clearance fit, right? Because that rack has to, or that RAM has to go up and down, okay, freely. So it's going to be another clearance fit. And again, you're going to reread it for that depth of cut. Is it going to be the same as the width? Maybe. Is it going to be different? Maybe. You're the designer. You get to pick. Okay. Isn't that fun? Yeah. Now here again, you're going to notice that there are dimensions that they're using, but based on what we're going to do, they don't have a dimension here for the depth of cut. So guess what? That's going to be how you dimension it. So you're going to change the dimensioning scheme a little bit. Okay. Isn't this fun? You get a little bit more autonomy. Does that make sense? Okay. There isn't one definitive final answer. There's reasonable answers, okay? There's reasonable answers as long as you're making good assumptions and picking good fits that are appropriate. I can't say no, okay? But if you're way off, if it's like you picked an FN fit, an interference fit, and it should have been a clearance, well, that's when I have to be like, let's rethink this, or let's look at the operation and see what we want, okay? All right, so yes, both of those are going to be clearance fits. Clearance fits. Okay, let's go back. Next one. Pinion shaft diameter and the pinion bore in the frame. Okay, so again, going to be now this one is going to be a hole in a shaft. So pinion shaft diameter, all right? So if we look underneath, the pinion shaft is the one that has those gear teeth on it, okay? The pinion shaft side is going to be here. This is considered the pinion where we have our teeth. This is the pinion shaft. So it's this diameter right here, the back side. And that is going to fit through the frame on this side. And this is going to be, let's see, this is going to be the pinion bore. So it accommodates, this is a nominal size of 1 1/8. And this is 1 1/8. So it's going to go through on that side. So it's on the closer side here of that head portion, if you would. Okay. So it's comparing those two. Okay, so pinion bore is the hole that's in the frame, and the pinion shaft is that larger diameter on the pinion shaft diameter, 330. Okay, so again, in this case, as we look at the operation, clearance or interference. We saw him stick it inside, right? Was he able to freely put it in? Yeah, right. So that's going to be a clearance fit. Okay, clearance fit. Tyler, yes.
Would it make more sense to put it smaller in since we're putting, that's the one that's.
Oh, that's coming, Tyler. This is the side that's called the pinion shaft diameter. So it's to fit the larger hole on this side here. Okay.
Why would there be a big hole here if we're.
Because this has to fit in the inside to engage with that RAM. So,
That hole is way too small for that RAM to fit in. The RAM is 0.75 square, while the hole is 0.515.
the RAM isn't going in the hole. The pinion shaft is going in the hole on this side right here.
Yeah.
Right. So there's a 1 1/8 inch bore, and there's a 1 1/8 inch-ish nominal size pinion shaft. It's this side of the pinion shaft, this part right here. So it's this fit. This part fits with that hole. Okay. So that pinion shaft right here is gonna go in this side. The smaller diameter is gonna be here. The larger diameter is gonna be here. Okay,
All right, now
you see it? Yeah, and that's part of this too, kind of seeing how these things go together. Also, I've got the Arbor Press here in the room that we can kind of take apart and you can kind of see how these things go together. So feel free to do that as well. Okay, so that is that one. Now, the next one is going to be the collar ID to fit over the shaft extension on the pinion shaft. So if we go back over here, the pinion shaft has this smaller extension. That's the 3/4 inch diameter that's sticking out. That's going to go through here and it's going to stick out the end over here. And to hold it in place, there is this collar right here. So the ID, the inside diameter of this collar, needs to fit over the extension on our pinion shaft. Okay. Now, in that collar, as we saw in the video earlier, there's a set screw that's going to lock it, if you would, or keep it on the shaft. Okay. So you are going to do the fit on the ID. Again, it's giving you limits already. Ignore those. Just go nominal size. In this case is 3/4 of an inch. Okay. It's going to fit over the end of this shaft extension, 3/4 of an inch, and you're going to pick a fit that's going to be appropriate for that. Okay. Clearance or interference? What do you think? Probably clearance, but now you got to think, do I want that to be a sloppy fit or do I want it to be a relatively close fit? That's going to be something you have to think about. And again, we've got it here. So if you want to kind of compare and look, we've got the Arbor Press here. Okay. So the class of fit within the clearance is what you want to target it on. Okay. So good. Pinion shaft extension. That's the 3/4 inch to fit inside the shaft bore of the frame. So this is the other side. So this is the pinion shaft extension right here. And that is going to go and fit right here in this diameter. We see that diameter called out as the 3/4 inch diameter here. So it's a nominal size of 3/4 inch. And you're going to specify the fit of the shaft bore. Yes, there's limits here already, but we're ignoring those. We're going with nominal size 3/4, nominal size 3/4, and now you're going to pick a fit to make that work. Clearance or interference? Clearance, right? Yeah. Maybe clearance fit. Okay. Back over here. Groove pin to fit in the hole of the table plate. Groove pin to fit in the hole of the table plate. So if we go back here, the groove pin is this little pin right here. Okay. There is a little cutout there. It's not even giving you the dimensions for it. Just model this as a single pin. That's all that you have to do. Outside diameter of about 1/4 of an inch and a length of 0.875. That pin is going to fit into the hole that's right here in this table plate. Okay. This fits on the top of our, I don't know, the plate, if you would, the foot, the base of our Arbor Press. Okay. This pin sticks out of the bottom and it's going to rest inside of the hole here on that base. Okay. What we want to know is what is the fit between this pin and this table plate. That table plate and that pin need to stay together all the time. Okay. Because we can take it on and off and that pin is going to stay in there. Interference or clearance? Interference. We don't want that pin to fall out. We always want it to be part of, we want to be part of that table plate. This is the subassembly you're going to create, okay? When I talked about it in the assemblies, there's going to be a little subassembly. It's just 2 pieces, but we want those always to be together, okay? So in that case, they're going to be a press fit, okay? So when we go back over here, you're going to be picking out then the appropriate fit. So it's going to be an FN something, right? FN something. So you can read the descriptions and see what you feel is most appropriate. Number 7, now we're going to look at the fit between that same groove pin. And we want to see how it's going to fit into the base, the hole in the base of the frame. So remember, he took that table plate with the pin pressed into it, and he was able to freely put it on and off here, right, within that hole. Interference or a clearance? Another clearance fit, right? Yeah. Yep. And again, you're going to notice that nominal size here is 1/4 of an inch, and they picked a size here for that hole. I'm going to see, oh, it's right here. Here's that size of that hole. That's the groove pin hole. They have a diameter of 0.265. Pick a fit and then apply according to that. So it might not be 0.265. It might be something else based on what you pick for your fit. Nominal size is 1/4 of an inch. Make sense? So good. And then that's it. So there's 7. Yeah, 7 of them. So once you get those done, now this is a place we're going to document those fits. So it's kind of like bringing that all to the front as you model, okay? Model to the nominal sizes, okay? So for instance, when you go to the diameter of this bore, that bore is a nominal size of 3/4 of an inch, okay? Model it at 3/4 of an inch. Then when you dimension your drawing, now you're going to apply the tolerances that you put on there. And remember, you can in the drawing identify a tolerances as a minus and a minus if you need to, or a plus and a plus, okay? And it'll put the appropriate limits, if you would, in the drawing itself, okay? So that is going to be the first part of what I want you to think about in terms of our arbor press, okay? So I'm going to go back over here. You are going to be ready. So I'm going to leave student view. I got to go back. So I think I have to go. Hold on. I might have to go back out of my course. Hold on. And then back into the modules. So if I go to module 2 here, based on what we have done this evening, you can do the 2 practice problems, the dimensioning review and the tolerances and fits that we just talked about. Now, if you're eager to get started, maybe many of you have, doing the models, I think is the best place to start on the arbor press. The next time that we're together, I will be going over in detail a couple options that you have with making the arbor press, okay, the frame, and the pinion shaft, okay, that pinion shaft, which those 2 I think are the most, if you would, complex, okay, ish, okay. If you're going to be doing the ram, there is a detail, and I'll show you where that is. I'll also go over that the next time, but this one's a little bit, I think, more self-explanatory. But if you go in here, there's a gear terminology handout, which is just below the arbor press video. And if you do the RAM, the second page of this gives you the details for that. Okay. So, so that's there for you if you wanted to, make that. Otherwise, we'll talk about that one the next time that we're together. You could make it like just the nominal sizes and make it just a rectangle and then add the teeth later after we talk about it. But everything else you could make already. Are there any questions? All right. The only thing that I'm going to mention here is that on this arm, I call it the arm on the frame. There are 2 ways that you can approach this, because I know maybe there might be a couple people that are ready for this. You could do a loft, okay, where you draw the cross section down here, and then you loft it up to a smaller cross section on the top, and then this would be the guide. The only problem with the loft, and I have done it many ways, is that it's not going to match perfectly the outside curve here, okay? When we look at the function of our arbor press, we can probably say that's not super critical, okay? That outside, that meaning this guide curve right here, okay? That's not super critical. The one that's more critical is on the inside here, because now this is where you're going to be placing things, okay? So if you are doing the loft and it doesn't perfectly go along the curve, that's okay, all right? Don't get too concerned about that. What you have to do is put more and more cross sections in order to make it meet it more closely, all right? And it's almost like infinite number of cross sections. If you want to spend time with a number of cross sections, that's totally fine. The other way to approach it is to make it a solid part and do the cuts, and then it would be exactly the right size. Okay, so I'm going to be demonstrating both ways and showing you both ways the next time we're together. But if you want to play around with that and approach that, that's totally fine. The other one that we see up here, the pinion, this one, I'm kind of excited about this because when I did it in Creo last time, we had to generate the teeth, the profile of the teeth using the equations for a spur gear. But the way that we can do it in SolidWorks is we can actually use the toolbox to grab a gear route and then adapt it to our part. So it's kind of an innovative way, and I don't know, I think it's kind of neat. So so I'll show you that process the next time. But if you want to play around with that too, you feel free to do so. So so that's what I have for tonight. So you've got a couple things that you can work on, a couple things that you can get started on as far as modeling, and then I'll let you guys use the rest of the time as you so choose. And I'm going to stop the recording. Gosh, it was a long one tonight. A long one.